This is the screencast for section 5.4, example 8. We're going to analyze antiderivatives graphically. Now, you have already done this, so please try and relate this back to chapter 4, specifically section 4.3, when you were relating graphs of a derivative to their antiderivative, like you were looking at f of x, f prime of x, and f double prime. This is the same exact thing, it's just now it's written in a different form, and I'll show you how that goes as we go through here. So, example 8, using the graph of f to analyze h of x equals the antiderivative from a to x of f of t dt. So right there, that tells me in terms of how you knew it before as f prime, and f double prime, they're saying h of x is the antiderivative of f. Okay, so I know we're using two f's here, but what this is saying is that the antiderivative of f is h, so the original could be h of x, the derivative then could be f of t in this specific situation. So if you're looking at position, velocity, acceleration, the position would be h, the velocity would be f of t. And we don't know f double prime, but that's okay. So, part A. Find h of 1. Okay, well, it says that h of x is the antiderivative from a to x. Oh no, it actually gives us a specific lower bound here. So from 1 to x of f of t, which we don't know, dt. It wants me to find h of 1. So h of 1 means I'm replacing x with 1. I'm replacing x with 1. See that? The x and the input of h got replaced. So I find x, which is up here, my upper limit of integration, and I replace it with 1. And as we know, the integral from 1 to 1, so a rectangle that has 0 width, is going to have an area, or signed area, of 0. Part B asks, is h of 0 positive or negative? Justify your answer. Well, first of all, h of 0 is the antiderivative from 1 to 0 of f of t dt. So I'm going to look at my graph. Here's the x value 1. If I'm finding the area, the signed area, from 1 to 0, so I'm going backwards, this area is above the x-axis, so it would have been positive if it were 0 to 1, but now it's backwards, so it's going from 1 to 0, it's going to be negative. So I need to put that in words. So what I said is, since the antiderivative from 0 to 1 of f of t dt is greater than 0 because the area is above the x-axis, that means, or then, the antiderivative from 1 to 0 of f of t dt is going to be the opposite of it and therefore less than 0. Part C asks to find the value of x for which h of x is a maximum. H of x is a maximum where its derivative, and we know this from chapter 4, changes from positive to negative, because then h of x would change from increasing to decreasing. Well, we know that the derivative of h of x is f of t. How do we know that? That's right, the fundamental theorem of calculus. So we need to state that first. We need to state the relationship in terms of derivatives. Right now it's in terms of integrals, but I only know the relationships between derivatives and antiderivatives if I put them in terms of f prime, f double prime. So I'm going to state that the derivative of h is f of t by the fundamental theorem of calculus. So now that I've got that the derivative of h is f, the graph we're looking at, this is the graph of f of x. So now, where the graph of f of x changes from positive to negative, I will find a maximum in h, and that happens at x equals 4. So I said h of x has a maximum at x equals 4 because h prime of x, which is f of x, changes from positive to negative, and therefore h of x would change from increasing to decreasing. Now let's keep going. D, find the value of x for which h of x is a minimum. Well, the same strategy is going to occur. We're still looking at the graph, remember, of f of x, which we have determined to be h prime of x, so don't forget that, the first derivative of h. So we want to find where h has a minimum. Well, if we're looking at its derivative, a minimum is going to occur where the derivative changes from negative to positive. Well, that really isn't happening on this graph of f, is it? So now don't forget, we can still look at endpoints. So let's look at the left and right endpoints here. At x equals 0, the first derivative is positive, which means the initial function would be increasing, creating a minimum there as a left endpoint. So we do have a minimum at 0. How about over here at 8? Let's see, the derivative is negative, so the original would be decreasing before a right endpoint, which would also create a minimum as an endpoint. Now, we don't need to relate f to h prime anymore because we did that on the previous example. This is still part of the same problem. We've already used the fundamental theorem of calculus to claim that the graph we're looking at is the derivative of h. So now we can just state that we have minimums as endpoints. So I explained these very similarly to how I would in chapter 4. I said that h of x has a minimum as a left endpoint at x equals 0 because h prime, the derivative, or f of x, the graph we're looking at, is positive after a left endpoint, and therefore h of x would increase after a left endpoint, and very similar phrasing for the right endpoint. Part E asks to find the x-coordinates of all points of inflections of the graph y equals h of x. Okay, so points of inflection, back from chapter 4, can be found in the second derivative, where the second derivative changes from positive to negative. But we don't have the graph of the second derivative here, so we have to look at the first derivative, and if you remember, points of inflections also occur where the first derivative, therefore, changes from increasing to decreasing, or decreasing to increasing, because that would mean the second derivative changes from positive to negative, or negative to positive, respectively. So, find the x-coordinates of all points of inflection, and we're going to do that by finding out where the graph of f, the derivative of h, changes from decreasing to increasing, because that means the second derivative would change from negative to positive inflection point. Therefore, we have inflection points at 1, 3, and 6. So I said that h of x has inflection points at x equals 1, 3, and 6 because h prime, which is f of x, the graph we're looking at, the derivative, changes from increasing to decreasing or decreasing to increasing at those x values, and therefore h of x would change concavity, giving us inflection points. Now I stuck in an extra part f. I would like you to sketch h of x, and you can sketch it right on this graph here. Remember, we're going to do an increasing, decreasing pass and a concave up, concave down pass. So maybe I want to do that on a little sketch down here in the right corner. I can make that myself. So as far as my increasing, decreasing pass is concerned, the derivative of h, which is what I'm looking at, I've established that from the fundamental theorem in part C. So the derivative is positive, and then 0, and then positive again. So we've got increasing, flat, and then increasing again all the way to 4. Then at 4 we change to decreasing all the way back to 8, or out to 8. Concave up and concave down. Concave up occurs when the first derivative is increasing. Concave down occurs when the first derivative is decreasing. So we have concave down from 0 to 1, then concave up to 3, then concave down all the way to 6, and then concave up from 6 to 8. So now I'm going to translate that into my graph of h of x. So between 0 and 1, I'm increasing, concave down. Doesn't matter where I start. It didn't give me any initial value or anything, so I'm going to start here. Why not? Increasing, concave down. I have a horizontal tangent right there at 1, but then I'm increasing now concave up until 3. At 3, I am still increasing, but I change to concave down until 4. At 4, I change to decreasing, but still concave down all the way to 6. At 6, I'm still decreasing, but I change to concave up until 8. And there's a rough sketch of what h of x would look like. I'm going to go back here and define h of x as the antiderivative from 1 to x of f of t dt. So this does actually give us an initial value. Here's where this is different than chapter 4. If I plug in 1 for x, I get the antiderivative from 1 to 1, which is 0. So I need to take this graph and make sure that 1 has a value of 0. Now the rest of the values, that's kind of unclear. I can tell a little bit about the area eventually, and we will build on that, but for right now, worry about that initial value. The antiderivative from 1 to 1 is going to be 0. So that means when you plug in 1, h of 1 should equal 0. We actually said that in part A. The now try problem 57 takes us through the same similar steps. We're going to have this function h that is defined as an antiderivative of f of t. So we're looking at f of t, which by the fundamental theorem of calculus, that'll come up later, is the derivative of h. All right, so now part A, find h of 0. H of 0, so instead of h of x, h of 0 is going to be the antiderivative of 0 from 0. We're plugging in 0 for x of f of t dt, and then the antiderivative from 0 to itself is 0. So that's kind of our initial value, 0, 0. The graph of h is going to pass through 0, 0. Part B, on what interval is h increasing? All right, well, h is increasing where h's derivative would be positive. So I need to now use the fundamental theorem of calculus to state that f is the derivative of h. By the fundamental theorem of calculus, the derivative of h is f of x. So since f of x is positive on the interval 0, and I included that because at 0 the value is 8 here on f of x, so from 0 to 6, h of x would be increasing there. Part C, on what interval is the graph of h concave up? Well, h is going to be concave up where it's first derivative, where h is first derivative, so f is increasing. F is increasing from, let's call that 9 to 12. And I didn't need to use the fundamental theorem of calculus again to establish that the derivative of h is f, the graph we're looking at, because I already did in part B, so I'm just kind of going off of that, or that claim that I've already made. Part D asks us a new type of question. Is h of 12 positive or negative? Well, h of 12 is going to be the area from 0 to 12 of f of t dt. So the signed area. So here's the positive area, here's the negative area. It looks like there's more positive area than there is negative area. So I'm going to say h of 12 is going to be greater than 0. So positive, because there's more positive area above the x-axis than there is negative area below the x-axis on the interval 0 to 12. Part E, where does h achieve its maximum value? That is not asking for any maximum. It's saying where is h's maximum, its absolute maximum, and it wants you to explain. Okay, so then h, we have to first find potential maximums, and then we can see where the absolute is. So a maximum of h will occur, let's see, in the middle of the function when h's derivative, so the graph we're looking at, changes from positive to negative, so h would change from increasing to decreasing there. So there's a maximum possibility at 6. Now what about those endpoints? The left endpoint, the derivative is positive, so that would be, h would be increasing after a left endpoint. That's a minimum, so we'll keep that in mind here for f. And then how about negative before a right endpoint? That would be decreasing, h would be decreasing before a right endpoint. So that would also be a minimum. So our endpoints here are minimums. We'll have to keep that in mind for part f. So where does h achieve its maximum value? Well, its maximum value is going to be the only maximum it has at x equals 6. So h has a maximum at x equals 6 because h's derivative changes from positive to negative there. Now since this is the only maximum of h, x equals 6 is the absolute maximum of h, so h achieves its maximum value at x equals 6. So part F, where does H achieve its minimum value? Okay, well we've got two possibilities for minimums, 0 and 12. So first we're going to state that claim. So I stated that H has a minimum at x equals 0 because its derivative is positive after a left endpoint, so H would be increasing after that left endpoint. And then H has a minimum at x equals 12 because f of x, the derivative of H, is negative before a right endpoint. Oops. So H of x would decrease before a right endpoint. Alright, so now out of these two endpoints, x equals 0 and x equals 12, which one is the absolute minimum? Because the question's asking us, where does H achieve its minimum value, its complete minimum value? Well, from part A, we already established that H of 0 equals 0. And then from part D, we established that H of 12 is greater than 0. That means x equals 0 has to be the absolute min of H. If H of 0 equals 0 and this one's greater than 0, the lowest value is going to be at H of 0. Now part G I added on. Let's sketch the graph of H of x. So I'll do my increasing and decreasing pass, which is actually pretty simple. F of x, which remember is the derivative of H, is positive between 0 and 6. So then H of x would be increasing between 0 and 6. Now remember, H of x starts at 0, 0. That's our initial value. When we plug in 0, we get out 0. So we're going to increase from there. And then, it looks like this is about an 8 by 6 rectangle cut in half, so you could say that's about 24 units. So you could say that H of 6 is 24, approximate area under the curve, but we're not there yet, so we'll just say between 0 and 6 it increases. We don't need to give a scale on the y-axis as long as our initial value is correct. Then the derivative of f is negative, so derivative of h is negative, f of x, between 6 and 12, so we'll decrease there. Now concavity. The derivative of h is decreasing, so concave down, between 0 and we said 9. So we've got a inflection point here at 9, all concave down there, but then increasing from 9 to 12, so we're going to go concave up then from 9 to 12. So now I can use this to sketch my final graph. Starting at 0, 0. From 0 to 6, the graph is increasing concave down. And then from 6 to 9, decreasing concave down. And then from 9 to, 12, decreasing concave up. So we also kept in mind that H of 12, remember, has to be greater than 0, and it is. It's a little bit greater than 0. Technically, its exact value would be whatever the area above the x-axis is minus whatever area is below the x-axis, but they look kind of close, so maybe 2 units, I don't know.